Hardy will tell us everything we are doing wrong. So Hardy, thank you very much for being here, and the word is yours.
Thanks, Antonio. First of all, I want to thank the organizers for this wonderful program. It's really a pleasure and to be part of it. And I very much regret that I couldn't come in person for complicated bureaucratic reasons. So I will today start with just a brief outline of the current status of ab-initio theory of superconductivity. So that's with respect to our favorite, which is superconducting DFT. And as an example, I will show you a calculation of a rather complicated material, which is niobium diselenide, that has a competition between a charge density wave and superconductivity. Then I will show you a little bit about what we can say on the order parameter, how it looks in real space. And this may or may not ultimately lead to something like a descriptor of superconductivity, may be useful in machine learning and other techniques of that kind. And finally, I come to the main topic, which is the ab-initio approach to non-adiabaticity. So DFT for superconductors, you all have seen it before. The basic idea is to include the order parameter of superconductivity as an additional density into the ordinary DFT formalism. Now, if you want to describe phonon-driven superconductors, you also should do something about the nuclei. So we include the nuclear n-body density matrix, the diagonal of the nuclear n-body density matrix, as a third density in the formalism. So this is the Hamiltonian. Here we have the three densities: ordinary density coupling to a scalar potential, the order parameter coupling to a pairing field, and the nuclear n-body density matrix coupling to a nuclear n-body interaction. So that's the three densities here. And one can prove Hornbeck-Cohn-Merman theorem for superconductors that these three potentials are in one-to-one correspondence with the three densities in thermal equilibrium. And then this leads to a set of Kohn-Sham equations. The electronic one looks like a Bogoliubov equation, and the nuclear Kohn-Sham equation is an n-body Schrödinger equation with an n-body interaction. So these three potentials, the scalar Kohn-Sham potential, the pairing field, and the nuclear n-body interaction, they are all functionals formally of the three densities. And in practice, the challenge is to find good functionals for those. And just from the start, I should say, we use for the nuclear n-body potential here the ordinary Born-Oppenheimer potential energy surface mostly, but this is exactly part of the topic that I'll come back to later. And then we do the usual harmonic approximation, diagonalizing the Hessian and get the phonon spectrum. But in principle, this dependence on the order parameter allows you to describe things like a change in the phonon frequency at the transition from the normal conducting to the superconducting phase. Likewise here, for this potential, we use the ordinary Kohn-Sham potential in LDA or GGA approximation. So the only real challenge is to approximate this guy, the pairing potential, as a functional of the densities. And for this, we use many-body perturbation theory. So the diagrammatic formalism is based on a particular version of perturbation theory where the unperturbed system is the Kohn-Sham system. So that's the electron Bogoliubons here and the phonons. So there's some normal and anomalous electron propagators and the phonon propagator associated with this Hamiltonian, leading to this 2x2 Nambu-Green's function. That's the Kohn-Sham-Green's function. And so the Kohn-Sham system, like always in DFT, is constructed in such a way that it reproduces the densities of the full system, of the fully interacting system, which means in particular that here the order parameter can be calculated from the off-diagonal part of the Green's function, the full Green's function, and likewise of the Kohn-Sham-Green's function, and they should be the same. So G without the index S is the full Green's function. Now, to actually make progress and find a way of calculating the anomalous Kohn-Sham potential, we use the Dyson equation. So we just write down the Dyson equation for the Nambu-Green's function, take the equal time limit of the Green's function, and use the fact that for the Kohn-Sham-Green's function and the full Green's function at the equal time limit, they are the same. And this leaves us with this equation. In the normal conducting case, this is called a Sham-Schlüter equation. And here we have extended it to the superconducting case. And what this does is it is a connection between DFT and many-body theory. So for any given approximation for the self-energy here, we can, by solving this equation, get the corresponding approximation for the anomalous potential. And so we need as input an approximation for the self-energy, and for this we use the standard Migdal-Eliashberg self-energy as written down here. So that's the electron-phonon coupling matrix, and that's the phonon propagator. And this then leads to a DFT-like gap equation where the kernels here, Z and K, are explicit expressions that follow from the formalism. So there's no free parameters. That's the equation we have to solve. Now, compared to the full Eliashberg formalism, this is, of course, a much simpler equation because there's no frequency dependence. There is, of course, retardation, but it's not visible, right? It's hidden, so to say, in these terms here. Now, by virtue of the Sham-Schlüter equation, the Kohn-Sham order parameter, this is really by construction, is the same as the one obtained from the Eliashberg theory. And hence the temperature where the order parameter vanishes, so in other words, the critical temperature, should also be the same. And in fact, numerically, that's pretty much the case. There are some little deviations, but not important. Now, the same cannot be said for the gap function, because the Kohn-Sham gap function is not expected to really be the true gap. So for this, we need a functional approximation, and this is the approximation that we need. So to summarize this aspect here, this Kohn-Sham DFT gives you, by construction, the same critical temperature as Eliashberg theory would give you, while the gap has to be approximated with a further going approximation with a functional approximation. So here's what you get. This is what you should look at is for the critical temperatures here, the green bars compared with experiment, that's the black bars. And as you can see, this is the agreement is for these materials here, always within a few percent. So it's really a predictive theory, right? The comparison here is with the red bars, which is a previous function L, which is not quite as good as you can see here. So that's where we use, just to go back, in the self-energy expression, the Kohn-Sham propagator here. So that's an approximation that does not satisfy Migdal's theorem. So, and yes, it's less good if you compare critical temperatures. And this is now the results for that function L of the gap function. And as you can see, it's pretty good compared to experiment. So you compare these black dots, that's various experiments with the green bar. Okay, now, so the main advantage if you are interested in critical temperatures of superconducting DFT, is really that it's numerically much simpler than the full Eliashberg equation. And this allows us to really deal with very complex systems. So this is niobium diselenide above 33 K. It has a relatively simple structure, so it's a layered structure which are van der Waals coupled. And each layer we have this plane of niobium atoms, which is a nice hexagonal plane above 33 K. This is a top view of the structure. So here you see the selenium atoms are a bit up compared to the planes of the niobium atoms. And this is, again, this full layer. Okay, now this is, and what I'm reporting here is a collaboration with an experimental group of Katharina Franke at the Free University Berlin. This is a high-resolution STM picture taken at the low temperature, so lower than 33 K. And what you nicely see here is a charge density wave. So if you look at these hexagonal motifs and go to the next hexagon and then to the next hexagon 6 times, you end up with this hexagon. And if you compare the first one with this one, here you see there's a bright dot in the middle. And here's nothing in the middle. Here you have these triangles which have no atom in the middle. Right? So these are two different motives, right? A hollow motive and a filled motive, so to say, and this repeats itself. So this is the modulation of the charge density wave. So it's not almost commensurate, I should say, not quite, as a deviation of a few percent, which is neglected in our calculations. So, but this is the thing that we really honestly calculate. This is now the Fermi surface. These slices correspond to different values of Kz. And the colors indicate here projections from the two motives, the hollow motive and the filled motive. So the colors, this is the hollow one, and this is the filled one in red and in blue. So you see which contributions comes from what, roughly. So it's a challenge to analyze this kind of complicated Fermi surface. So here in the top plot, you see a comparison with the structure above 33 K. So below is the charge density wave. Above, you have these very clear, nice blue lines. That's the simple Fermi surface above 33 K. And all this cabbage, these complex structures here, this comes from the charge density wave. Now, this is the K-resolved electron-phonon coupling, and this is the superconducting gap. And like always, they kind of look very similar. And so one thing that is very clearly visible here is that each part of the Fermi surface, each sheet, has a huge variety of gap values, right? So we can, as main results, affirm that, first of all, charge density wave and superconductivity do coexist here. And a two-gap or multi-gap scenario where kind of each sheet of the Fermi surface has one value, more or less clear-cut value of the electron-phonon coupling. That's not the case. That can be ruled out. Each sheet of the Fermi surface has a large variety of gap values. Okay, so this was K-space. Now let's take a look at the superconducting order parameter in real space. And this is now for much simpler systems. So this is the order parameter. And those are the Kohn-Sham orbitals here. Chi-n is related to the gap function in the usual BCS way, the usual BCS formula. And if you now look just for a second at the equal RR prime case, so the local order parameter, what you then see is this expression here for the local order parameter. It's the sum over the orbital squared, those orbitals that are at or near the Fermi surface. And this is, if you go back to this formula, because the order parameter is extremely sharply peaked near the Fermi surface. So making the approximation that this is kind of a delta function at the Fermi surface, the order parameter is mainly given by the orbital squared, those orbitals whose k vector is on the Fermi surface. So this is for MGB2. Now you realize that the full order parameter is a function of r and r prime, so one can rewrite it as the average, as a function of the average coordinate and the relative coordinate. And so we call this R, capital R and S. So for S equals 0, we are back to the local order parameter. And this is what is plotted here. And what you nicely see here, right, it's the orbitals, as I demonstrated before. This is the sigma bond in the boron plane, which you nicely see here. For different values of S, right, you still see the hexagonal symmetry, but the picture looks a bit different. Now this is for MGB2 from a side view. So here again, in the planes, you see these sigma bonds. So this is where the order parameter lives, right? The order parameter superconductivity lives in the chemical bonds, right? So of course we have known this for decades, but it hasn't really been explored much, I would say. So another example, calcium C6. So you nicely see the p orbitals here. And now what can we say about the dependence on r minus r prime on this coordinate S? So of course in K space we have this strongly peaked structure, and in the one-dimensional case you immediately realize that this double peak structure, its Fourier transform, has oscillations. And in fact, that's what we see also in 3D. So this is now the order parameter. It's again MGB2 as function of S, with capital R being fixed, in this case, to the center of the boron hexagon. So here you see blue is negative values, bright yellow, orange is positive value. You nicely see these oscillations. This is where R naught is in the middle of the boron bond. And right, and this is in the middle of the sigma bond. So again, these very clearly visible oscillations. Okay, so what can we do with this? So we know chemical bonds, the Kohn-Sham orbitals, ultimately, this is what the order parameter is. That's where the order parameter lives. That's where superconductivity is. Can we find a correlation with these bonding properties, correlation of Tc with bonding properties? And for this purpose, we investigated, we looked at 4 different compounds, which are structurally very similar. Both the structure and the electronic structure is very similar, but the critical temperature is vastly different. So this is MGB2, the usual Fermi surface, 2-band superconductor. And this is calcium, beryllium, silicon, very similar. There's a slight difference. Here's a little pocket in the Fermi surface where the electron-phonon coupling has a different value. So this is actually a 3-band superconductor. But the main difference is, if you look at it closely, the localization of the sigma charges in the sigma bonds. So here, this is not very localized. Well, here it's localized. And this is the general trend that we find. And in fact, it's plausible that lambda correlates with the strength of the sigma charge localization. We find this in many systems. Now, one might say that's kind of expected, right? If you localize the charges more, electron-phonon coupling becomes larger. But then one might argue that at the same time as the phonon electron-phonon coupling becomes larger, also the Coulomb repulsion becomes larger, right? So these two effects should counteract, right? But what we find is that the correlation with the Coulomb repulsion is indeed there, but it's much less pronounced. And this is analyzed in great detail here in this old paper with Andrea Flores, Antonio, and Gianni. So this is what we find, and well, maybe this might serve, if you condense this degree of charge localization into a single number, might serve as a descriptor of phonon-driven superconductivity, although we don't really calculate the phonons if we just look at this degree of localization. So this might be useful, and we are currently exploring that. Okay, so now the main topic. In the currently available functionals of superconducting DFT, what is missing there? So first of all, strong correlations are missing. So by that I mean that if you take of the current functionals the normal conducting limit, then these functionals reduce to standard LDA and GGA. So you have a poor description of the normal conducting parent material if that is strongly correlated. Then another aspect that is not captured is by our current functionals is non-adiabaticity. So a slightly vague definition here of non-adiabaticity is the coupling of electrons and nuclei beyond the Born-Oppenheim approximation. So what I exactly mean by non-adiabaticity, I will say in a minute. It's actually a large part of dealing with this kind of phenomena is to find a proper way of defining non-adiabaticity. So there's all kinds of things in the literature, more or less vague, all of them. And there is actually a way of capturing that very precisely. And this is what I will be talking about in the next minutes. And finally, anharmonicity is also missing. And I will show you a way which ultimately is a set of equations that can capture both non-adiabaticity and anharmonicity in a rather straightforward way. So just to say a little bit about what non-adiabaticity is, some examples here, by no means complete list. So the first manifestation of non-adiabaticity is decoherence. Right, so this is when you manipulate a many electron wave function, for example. So manipulating means you excite in one way or another. And then one realizes that this many-body state doesn't stay the way it is. In fact, very fast on the scale of the so-called decoherence time, it becomes a classical state. And in fact, it's this aspect that prevents quantum computing so far. So it's a very common thing. Decoherence is absolutely everywhere, usually neglected in our field of research. Then there's something in superconductor, inverse isotope effect, that was studied by Balatsky. Then there's non-adiabatic corrections to the electronic band structure, the famous twiddle near the Fermi surface in metals. Then there's non-adiabatic corrections, to the phonon spectrum as well. So Matteo, Gianni, and Francesco have been pioneering this. And then another aspect that I will discuss in some detail is that within the adiabatic limit, you cannot calculate electronic currents that are associated with nuclear motion. Then photochemistry, not so much of interest in our field. But then there's something that very much touches our field, and this is calculations of laser-induced structural and electronic phase transitions by Cavalieri and others. So this exists already in experiment. By shining a laser, you can induce, for example, a structural phase transition of the system, or an electronic phase transition from a normal to a superconducting, highly excited state. And how do you describe this, right? So the typical picture is you kick the electronic system up, it lives then in a Born-Oppenheimer surface, moves there, and then comes to a region where it couples to another surface, and then it moves to the other surface, which is a non-adiabatic transition. You go from one electronic state to another electronic state, for example, a superconducting state, but it's a non-adiabatic transition, so it's not triggered by external fields. Okay, and finally, a huge field of topology in R space. So this is not related to topology in K space or topological insulators and so on, but it's related to the molecular barrier phase. So the parameter here is the nuclear positions. So this is just a small list. So how can we capture this in an ab-initio sense? So if we go back to the full Hamiltonian of electrons and nuclei, with the kinetic energy of nuclei and electrons and the Coulomb interactions, then in principle we have to solve with this Hamiltonian the full problem. Of course, nobody can do that, and but it's useful to start from there and to define what we mean by non-adiabaticity. So in a first step, it's useful to neglect in that Hamiltonian the nuclear kinetic energy. So the nuclear positions are then just parameters here. And we imagine solving this many electron Schrödinger equation for clamped nuclei. And we imagine doing this for many nuclear positions, which in practice we cannot do in a solid. But just conceptually, let's think about this. And then the eigenvalues and the eigenfunctions become functions of the nuclear positions. That's a famous Born-Oppenheimer potential energy surfaces. And then in a second step, we make what is a useful definition of the adiabatic approximation. Namely, we take one such Born-Oppenheimer state. So this is a correlated many electron state for many capital R, for many nuclear positions, and multiply it with a nuclear wave packet. And this nuclear wave packet is coming from a nuclear time-dependent Schrödinger equation where the Born-Oppenheimer surface that is related to this one Born-Oppenheimer state is the scalar potential in the Schrödinger equation for this nuclear wave function. And of course, one can also look at the static limit when there's no time dependence, if the initial condition is right, then this just becomes a vibrational eigenstate of that Born-Oppenheimer surface. And this is, of course, what we always do when we calculate phonons. So a single Born-Oppenheimer surface and vibrational eigenstate. This is standard phonon spectroscopy. Now, this what I defined here as adiabatic approximation, where does it come from? So what is neglected? And this is the crucial thing. If we want to go beyond Born-Oppenheimer, we need to know what is neglected. Right? And that's useful to represent the full wave function in this so-called Born-1 expansion, where we expand the full wave function in the complete set of Born-Oppenheimer states. So this is exact formally. And the interesting aspect is that then, since the Born-Oppenheimer states depend on capital R, these expansion coefficients also depend on capital R. If one plugs this back to the full Schrödinger equation and multiplies from the left with the Born-Oppenheimer state, this is what one gets. So first line is actually that Schrödinger equation that we got from the adiabatic approximation. But then there's further terms, and they involve a coupling of all these coefficient functions, nuclear amplitudes, and the coupling is mediated by these so-called non-adiabatic coupling matrix elements. These are weird guys. So here's a nuclear momentum operator acting on the subscript of a Born-Oppenheimer state, first order and second order derivative. Now, you see here immediately, if these guys are small, if they are negligible, then we are back to the adiabatic approximation, right? So we can ask ourselves, is that actually a good approximation? And indeed, if you look at these matrix elements, they are mostly exponentially small. Only in the vicinity of intersections with other Born-Oppenheimer surfaces, they're not small. And there they can actually diverge. So if we do vibrational spectroscopy, where we are close to the minimum of a potential energy surface, so crossings with other surfaces are far away, and this is actually a very good approximation, right? So this is the ingredients, once again. Born-Oppenheimer equation, which gives you the surface, and then the solution of this wave packet moving in that surface. Okay, so this is the basis of all vibrational spectroscopy, our standard calculations of phonons. Now, there is one dramatic failure of the adiabatic approximation, which is very instructive. If you try to calculate the electronic current density, local current density that is associated with the nuclear motion. So if you have a coherent phonon, right, so nuclei are vibrating, and of course the electrons move with the nuclei, they vibrate too, that's obvious. If you try to calculate this local electronic current, this is written down here, you just calculate the expectation value with respect to this adiabatic wave function, with respect to the electronic current density operator. This is what you get. There's an imaginary part of this derivative expectation value, and that's zero because the Born-Oppenheimer states are real value, unless you have degeneracies. But degeneracy is the conical intersection. So if we are far away, then these guys are real, and these electronic currents are zero. And this is, of course, a complete disaster. It's completely wrong. So it's a dramatic failure of the adiabatic approximation, because these currents obviously are not zero. So when the adiabatic approximation fails, then what can we do? Well, in principle, we can go back to the Born-Huang expansion, and for small molecules, this can be done. But for larger molecules, and for sure for solids, it's just impossible. We cannot do this. So can we find an alternative way of going beyond the adiabatic approximation that does not involve the Born-Huang expansion? And this is indeed possible. And this is going under the heading of the exact factorization. This lives on the the simple fact that the exact full wave function can be written formally exactly as a single product. So that's not an infinite series, a single product of an electronic state and a nuclear wave packet. So this is now not a Born-Oppenheimer state. In particular, in general, it's time dependent. And so here in comparison is the adiabatic approximation, but it looks a bit like the adiabatic approximation. And if you plug this into the Frankel variational principle, then the full problem of electrons and nuclei exactly without approximation decomposes in a problem of electrons and a problem of nuclei. And they're exact, formally exact, and they're coupled. You will see the equations in a minute. And this, in fact, ultimately does allow us to do calculations for beyond the adiabatic approximation, also for solids, because the equation here is pretty much the same as in the adiabatic case. Right? It's an n-body Schrödinger equation. which we can treat then again in harmonic approximation, for example. Okay, so here's the sequence of theorems. That's the first theorem, that this is in fact an exact representation of the full wave function. And the crucial point is that this wave function is normalized to 1 for each fixed nuclear position. So it's a conditional amplitude like the Born-Oppenheimer state, but the Born-Oppenheimer state is an approximate conditional amplitude, while this is the exact conditional amplitude. Okay, so here are now these two equations. The nuclear equation is a nice Schrödinger equation. The electronic equation has a Born-Oppenheimer part and some rest that looks complicated. So the difference, let me highlight the difference to the adiabatic approximation. So first of all, there's a vector potential here now, which we didn't have in the adiabatic approximation. Then this potential energy surface, the scalar potential energy surface, becomes time dependent. There's a time dependence in the electronic equation also, which is not the case in the Born-Oppenheimer equation. And in addition to the Born-Oppenheimer Hamiltonian, there's this term here. So it at first sight looks horrible, this term, but well, keep in mind, this represents in a formally exact way all these infinite terms, infinitely many terms of the Born-Wang expansion that we have neglected. So this makes it look much nicer. So if you look at this here, clearly there's a coupling between these two equations. This term involves the nuclear wave function. And this couples to the nuclear momentum operator. So this gradient acts on the subscript here. So strictly speaking, this is not an operator again. It's a bit like a time derivative, like in the time-dependent Schrödinger equation. It's a weird object. Very importantly, this object is non-Hermitian. It's a non-Hermitian operator. And nevertheless, the time propagation conserves the norm. So this is an interesting fact. And it's exactly this non-hermiticity, but combined with unitary propagation, that leads to decoherence. So this allows us to capture decoherence in an ab-initio fashion, as I will show you in a second. Now, I didn't say yes. Yes?
5 more minutes.
Okay, that's fine. So I didn't show yet what this vector potential is. So it has the structure of a Berry connection. So here's the nuclear momentum operator acting on the capital R, and integrated out are the electronic degrees of freedom. And the time-dependent potential energy surface is the expectation value of the Born-Oppenheimer Hamiltonian with respect to this time-dependent electronic wave function. So there's an interesting, I will skip a few things here, that in the time derivative of the nuclear momentum and nuclear angular momentum, so this is Ehrenfest-like equations, you find forces that involve, on one hand, an electric-like term given by the gradient of this time-dependent surface plus the time derivative of the vector potential. So it looks like classical electrodynamics, but it's not, because this vector potential is this Berry connection. And in addition, there are Lorentz-like terms that come from the curl of the magnetic field. And they can actually be large. So in a system, when you have a neutral atom entering a magnetic field, this Berry connection completely compensates the external magnetic field. Okay, now on the exact level, the electronic nuclear equation of motion is, well, it's equivalent to the full Schrödinger equation. So that is nice, but it's not per se useful. But the crucial advantage is that then we have these two separate equations for the electrons and the nuclei, and this allows us to make approximations that otherwise one would not be able to do. And one prime example is where we treat these terms that go beyond the Born-Oppenheimer Hamiltonian in perturbation theory, right? This is a natural thing to do, especially there's a small prefactor, which is the electronic over nuclear mass ratio. So this lends itself immediately to do perturbation theory. And in this way, we can actually fully solve this conundrum of calculating electronic current densities that are associated with nuclear motion. So this is a model system where there's a tunneling process of nuclei going from one side to the other. And this depicts in that model, exact electronic local current density. This is the quantity which is strictly zero in adiabatic approximation. And if we treat this in perturbation theory, as you can see, the electronic current density here is very close to the exact one. So this solves really a 20-year-old problem in quantum chemistry. And this is measured, in fact, in vibrational circular dichroism. I won't discuss that in detail. Then, starting again, just one more minute, from the electronic equation of motion, another way is to represent this in terms of nuclear trajectories and to somehow density functionalize the first equation. And in this way, the most interesting aspect is that we can treat decoherence. So this is an off-diagonal element of the electronic density matrix, which should go to zero as a function of time, but it doesn't if you do standard techniques. But with this ab-initio way of treating decoherence, we can nicely capture this. Also in real world molecules, here you see the same effect. Okay, and finally solids. There we again start from these equations, but transform them into a set of Bogoliubov equations. It's for the electrons the natural thing to do, right? If we want to deal with superconductivity. For the phonons, it's not so natural to do, but we also transform this into a Bogoliubov equation for the phonons. So these are standard phonon creation and annihilation operators that are obtained from diagonalizing this nuclear equation. And there's a couple of interesting aspects here. This guy here, you can write it as a real part of F multiplying d plus d dagger. That's, of course, like always, the displacement, the nuclear displacement. But there's also the imaginary part of F multiplying d minus d dagger. That multiplies the nuclear momentum, but we know what multiplies the nuclear momentum. That's this baric connection vector potential. So that's the imaginary part of F that is captured here. And then in the time propagation, very importantly, this Bogoliubov matrix is anti-Hermitian. That's exactly what we want. If we want to treat a time propagation, then we excite the system, right? Exciting means we create phonons. So the number of phonons cannot be conserved. And so this is a desired effect. And finally, an important side remark here is that this Bogoliubov structure allows a mean field treatment of phonon-phonon interaction, so of anharmonicities. Right? If you have phonon-phonon interaction, so that's d dagger, dd, right? And these terms are immediately seen, and those are mean field expressions of capturing anharmonicity. So this set of two coupled Bogoliubov equations is useful to capture both non-adiabaticity and anharmonicity. That's the crucial point. And we have written these matrices here as functionals of the phononic and electronic one-body density matrix. And so far, this has been implemented by these people in the ELK code. For the static case, this is the functionals. I'm not going to discuss that. And the same set of equations yields both the renormalization of the band gap of insulators, the phonon-induced renormalization, and it yields the superconducting gap. So, of course, not really new results yet, but at least a new equation. And that's all I want to say. Thank you for your attention.